Alright, we're gonna try to get through this. So the big ideas of this section of chemistry are elements, atoms, and compounds, and chemical bonds. We'll also talk about water's life-supporting properties, but we'll talk about those in the next lesson. Okay, so we'll just focus on these two today. So to start off with elements, atoms, and compounds. So we need an essential question for our overall thing. So essential questions. What are electrons, elements, and compounds? Or electrons, atoms, and compound? And how do they bond? There we go. That's our essential question today. So to get started, we'll talk about how this relates to biology. So living organisms are composed of matter. Remember that any matter is anything that occupies space, and you might have learned that as volume, has space, and has mass, which is just stuff that makes it up, usually in grams. Okay. So matter is composed of chemical elements. An element is a substance that can't be broken down to any other substances by ordinary chemical means. So it's kind of the purest there is. It's in its pure state. There are 92 elements that occur in nature, but really only a few exist kind of purely that way. A lot of them exist kind of in compounds, really. So a compound is a substance that consists of two or more elements in a fixed ratio. So a particular compound might be like water, because we have 2 hydrogens for every oxygen. That's a fixed ratio. Compounds are a lot more common than pure elements because they're going to be a lot more stable. So not a whole lot of elements like to kind of be alone by themselves. They like to have other elements to kind of hang out with, and that's a bit more stable. Right? So another example of a compound, and this is probably a better compound, is sodium chloride, or table salt. It has equal parts sodium and chlorine. So it's in a 1-to-1 ratio. And we should know that one. Sodium in its kind of pure form, although it's not often found that way, but sodium by itself is actually a metal that's really soft and you can cut it with a butter knife. It reacts really, really violently with water, so it's a really reactive substance. Put it in water, it goes boom. Chlorine is actually a really, like a dense gas. It weighs more than air does, and it's like this yellowish, gross color. Again, very poisonous and would be very harmful to you. But when these guys get together and form a compound, it stables them out so they're not so reactive, they're a little bit nicer, and they form table salt, which is absolutely delicious. Okay, about 25 elements are essential for human life. 4 elements make up 96% of the weight of most living organism, and that's worth knowing. The 4 major ones are oxygen, carbon, hydrogen, and nitrogen. To remember those, I always think Chon. I don't know why, but it makes a word, sort of. Okay, but those are the 4 that make up 96%. As we get further through this unit, we'll talk about how those are related to are really major things like proteins and carbohydrates and fats, and even DNA. They're all mostly made up of those. Alright, then we have trace elements, which are essential but only really needed in minute quantities. So you only need a little bit of those. You need them, but just a little bit. So here are those 4 again: oxygen, carbon, hydrogen, and nitrogen. They make up a lot. Here's some other elements that we need in the human body that are all really, really important for survival. And then these are examples of trace elements down here. Okay, some trace elements are required to prevent disease, like iron. If you don't have enough iron, it's a disease called anemia. But you have to have iron. It sits in the middle of this thing called a hemoglobin, and it helps to transport oxygen. So you don't get enough oxygen if you don't have iron. By the way, if you've ever cut yourself and then put it in your mouth and you've noticed that the blood has a metallic taste, it's because of the iron. True story. We also have a thing called iodine deficiency. That's why you see iodinized salts in the stores. If you look at it when you buy Morton salt, some of it's iodinized, and it's to prevent this disease called goiter, because iodine deficiency prevents production of thyroid hormones. And thyroid's a little gland sort of in the neck area, and so if you don't have the iodine, there's a lot of swelling and just terrible time that happens, a lot of pain. Okay. Another one that we need is fluoride. Fluoride's usually added to municipal water, but you also find it in like toothpaste to help reduce dental decay. So fluoride helps make sure that you don't have cavities and stuff like that. Okay, so there's fluoride in toothpaste, and that's a good thing. All right, that's how I feel about it. We also have some other chemicals that get added to food. You don't necessarily have to write this, but this is an interesting point, is that several chemicals are added to food to help preserve it, or make it more nutritious, or make it look better. These are real all things that the people who buy foods, the consumers, this is what they end up wanting, and this is why things get added in ways that maybe aren't, always the best ideas. But you can always check out nutrition fact labels for at least the nutritious part of things to see on the foods and drinks that you purchase, which is hopefully not pasty and Cheetos. Alright, so you can check fat content, which we'll talk more about later. Cholesterols are under fats as well. The sodium content, which we know now is kind of the sodium ion, and we'll talk a little bit more about that here in a minute. But potassium, carbohydrates, so how much sugars are there, but you can also see all of these things that are added to it, including that important iron to ensure healthiness of who buys it. So that's the basic start of that. So I'm going to encourage you, this is a good place to take a break. It's not quite the 10-minute mark, but I would take a break, maybe pause, reread your notes, chunk them if you need to, and then come back. So a reminder on this section, I think you know some about this stuff, so really jot down the important parts and we'll move through it kind of quickly. Okay, so each element consists of one kind of atom, just one. Okay, like a gold bar as solid gold is just made up of one kind of atom, which is impressive. An atom is the smallest unit of matter that still retains the properties of that element. Okay. There are 3 subatomic particles in atoms, and sub means below, so it's kind of a category below the atom. And that's relevant to our discussion. We've got protons. We know those are positive. Electrons are negative. And neutrons are neutral. So hopefully that's a review for you. I hope that's not new. Okay, neutrons and protons are packed into an atom's nucleus. Now they live in the middle, and we'll look at a picture in a second. The electrons orbit the nucleus on the outside. And there's a little bit here, the negative charge of the electrons and the positive charge of the protons keep them close by. I think this is still up for debate. But the important thing is protons and neutrons are in the nucleus, and electrons orbit the nucleus. They're outside. Little reminders, so the protons make up the atomic number. And this is the identifying feature of that particular element. The number of protons is what identifies it. Okay? If you were to change the number of protons, you would change the element. And we don't want to do that. At least not right now. We can talk about it later, maybe, maybe not. Okay? An atom's mass number, so that's number of protons is the atomic number. The mass number is the number of protons and neutrons, because although the neutron is neutral, it does have weight, more or less. So it has mass, and it provides mass to that nucleus. The atomic mass is approximately equal to that mass number. It's more or less the same, but it takes into account isotopes. So in the nucleus, we've got protons, those are the positive. The neutrons, the neutral guys, and around the outside we have 2 electrons. So this guy is definitely helium because we know because it's got 2 protons. That's the identifying feature. Okay, we know that the mass number, so the mass number equals 4 on this one because we have 2 protons and 2 neutrons added together, so it has a mass of 4. The electrons don't have any weight on the outside, they just hang out there because they're in a cloud and they're there. It's like having a cloud around you. The cloud doesn't add to your weight. Okay. So although all atoms of an element have the same atomic number, right, because we have to have the same number of protons for that to be the element, so the atomic number and the element is identified by number of protons. Just to reiterate, we can have different isotopes of an element. So isotopes have the same number of protons but have a different number of neutrons. Okay, so different isotopes actually behave identical in chemical reactions because the neutron doesn't have any charge, so it doesn't affect the way that it interacts with other things. It just makes it a little heavier. Okay, so they react, react the same. You can say react the same as non-isotope, if you will. Okay. We also have these things, these radioactive isotopes. You don't necessarily have to write this, but it's an interesting fact, and we'll look at a cool video I have over it. I got a cartoon video that kind of explains this a little bit better, but radioactive isotopes, the nucleus will actually decay, and it gives off both particles of protons and neutrons. And it's really interesting, and it'll actually change the entire element or altogether. And they can be kind of dangerous because usually it's a really heavy atom that's got a whole lot of protons and a whole lot of neutrons in the nucleus, and so it's just not very stable. You know, you get too many people in the same room and it just doesn't get stable. You know, it's like taking all of Quest and putting them in the cafeteria and then expecting everybody just to be still and happy. Is that really going to happen? No. Okay, but we'll talk about that later on. We'll look at the video and make sense out of it. So here's some isotopes of carbon. So I guess quote-unquote normal carbon, or we've got carbon over here with 6 protons and 6 neutrons. The mass number would be 12. That's sort of normal, though sometimes there are isotopes of carbon like carbon-13, which has 7 neutrons, giving it a mass number of 13. And carbon-14, which gets used in carbon dating a lot, which we'll talk about eventually, has 8 neutrons, and that gives it a mass number of 14. Okay. But in all of them, they have the electrons the same. They still have 6 electrons because this guy is the thing that deals with reactivity. What makes it reactive. Okay, so they're the same reaction there. Quickly, you don't have to write this quite either, but some radioactive tracers are used in medical diagnosis because they don't react any differently and your body can't tell them differently from normal stuff. So we don't notice that it's a radioactive tracer. So it's been put into a body in order to look for heart disorders or cancer or brain. And one example of this is a PET scan. It's called the positron emission tomography. Crazy name, but this is the stuff that you see kind of on TV when we're looking for diseases and stuff. And it gives you a nice image so you can see what things look like inside a brain or, you know, elsewhere. There actually is a nice picture about this. This is what a healthy person would look like, and someone with Alzheimer's, this is how their brain would look through those radioactive isotopes that we could identify. So it could be helpful. It can also harm us because radioactive stuff actually does damage DNA, which kind of will lead to mutations and things that we'll talk about later, but radioactive stuff is damaging. So one of the early female scientists that we hear about, Marie Curie, she worked with radioactive uranium, and at the time they didn't know, so she didn't wear gloves, she didn't have any like protective gear, so she ended up with damage to her hands, just like cancer in the hand. It's sad, but she provided a lot for science. They just didn't have the protective gear that we have today. Okay, now we're going to look at chemical bonds. Yay! I like bonding stuff. I don't know. I just like the chemical bonds. It's a fun section. So remember, of the 3 subatomic particles, protons, neutrons, and electrons, only electrons are involved directly in chemical activity of an atom. So how reactive it is, whether it's going to form a bond with another atom or not, is totally dependent on electrons. Okay? Electrons are located in electron shells, and each with a characteristic distance from the nucleus. An atom can have 1, 2, or more electron shells depending on how fancy it is. Okay, information about the distribution of those electrons is found on your periodic table, which is great. And I've just talked to some of my junior avid students about this. You actually do have a periodic table in the back of your agenda. So if you ever feel like you need that bad boy, it's there. Okay, so again, electron shells, and you can see them, this information's in the periodic table. So we've got 1 shell for these guys, 2 electron shells for this row, and then 3 electron shells for this row. But when we talk about valence shells in just a second, the outermost shell, that's really the reactive part, and you can see that it's the same here and the same here. All these guys have 1, so they behave similarly. All of these guys have 7 on the outermost one, so they react similarly. Okay, so we'll talk about that. The number of electrons in the outermost shell is called the valence shell, and that determines the chemical properties of the atom. Really, my favorites, when you go back and look at it, these guys with 1s on the outside, is when you throw those things in water, they react and they explode. And the further you go down the periodic table, the more they explode, the more violent the explosion. There's all kinds of YouTube videos about it. Alright, so atoms whose outer shells are not full, so don't have 8, usually 8 anyway, tend to interact with other atoms in ways to enable them to complete it or fill their outside valence shells. They want to be full. They want to be like a noble gas, because that's kind of stability. That's where you want to be at. Okay, so when 2 atoms with incomplete outer shells react, each atom will share or donate or receive electrons so that both partners end up with completed outer shells. So everybody gets 8. Those interactions usually result in atoms staying close together and held by attractions that we call chemical bonds. Okay, so hopefully we remember chemical bonds from chemistry. In a covalent bond, so co means like together, so think like co-worker or cooperation. To cooperate, you have to operate together. To be a co-worker, you have to work together. So this is kind of like together. So a covalent, think of valent as meaning the valence or the outside kind of shell. So their outside shells are together. So when the outside shells are together, that means they share. So they're going to share a pair of electrons. Okay, that's how I look at it. 2 or more atoms held together by covalent bonds form a molecule. So molecules are held together by covalent bonds. A covalent bond, for example, connects hydrogen atoms together. Okay, in a molecule of the gas H2. So hydrogen has a bond with hydrogen. There you go. Okay, we'll look at the videos a little bit later. I've got some videos for you, I promise. But we'll look at those later. There are 4 ways to represent them that we'll look at on the next slide. Hydrogen atoms are held by a single pair of shared electrons, so that's a single bond. But the 2 oxygen atoms have 2 shared pairs of electrons. That's an easy one to confuse. And that forms a double bond. And double bonds are always stronger than single bonds. Triple bonds are stronger. The more things you share, the stronger that bond is. So like we share a classroom together, we share these, we share that classroom together and this kind of learning of biology together, so that maybe gives us a single bond. Oops, a single bond. But my dogs over here, which are pouty, they're currently sharing the lecture with me as well, so they're sharing in the biology knowledge, but they're also sharing my house with me. Okay, and I tend to share food with them too, so like not human food, but their dog food that I paid for. I share that with them. So now it's like a couple of things that we share together. So unfortunately, my bonds are stronger with my dogs. It's not offensive, they just live here. Okay. So here are the ways to represent them. You've got a molecular formula that you can use. That's the shorthand. You've got the electron distribution. It gets a little fancy, but it's closer to your Lewis dot diagrams if you remember doing those. Structural formulas, which are probably the ones I use most commonly. And then space filling models are the real crazy ones that fill stuff up. Okay. Covalent bonds join atoms into molecules through electron sharing. So hydrogen and oxygen are molecules composed of only one element. So that's one element. Whereas methane and water are compounds composed of two or more different elements. I think that's obvious. I don't know if you need to write that down, other than that should make sense. They're compounds with a couple of different elements, and those are just one. Okay? Atoms in covalently bonded molecules continually compete for shared electrons. So I got a little carried away there, I think, and we're going to talk about this one. But this might be a good time for you to, again, pause the lecture, take a little pause, put it on pause, and then go do some other things, and then come back to it. Maybe do look over your notes in that time and just double check it, maybe chunk some notes, write a few questions, and then come back to it. But this is probably a good time to pause. Okay, atoms in covalently bonded molecules, again, continually compete for shared electrons. Okay, they compete. So the attraction or pull for shared electrons is called electronegativity. And when I think of electronegativity, is it's like an atom's attractiveness. It's how pretty a molecule is. So if it's more electronegativity or more electronegative, it tends to be prettier. Okay, or hotter or whatever. Okay, but it's a prettier atom. And so it tends to use that to its advantage. So it's a prettier atom. Okay, so if we have molecules of only one element, the pull from each atom is equal because each atom has the same electronegativity. So think about those hydrogens again. These are two different atoms, but they have the same attractiveness. A hydrogen is equally attractive to a hydrogen. They're both equally pretty. So they're just going to share equally. So this is share equally because they're both equally pretty. And we call that a non-polar covalent bond because it doesn't actually form any ends to anything. They share equally. They just do, right? Water is a little bit different though because it's made up of a hydrogen and an oxygen. And these have different attractiveness. Believe it or not, hydrogen is much prettier. Oh, sorry, did I say hydrogen? I meant oxygen. I was thinking oxygen and I think hydrogen came out of my mouth. That happens. Alright, but oxygen is much prettier. It's more attractive. It's pretty. And it knows it. And so it's got a little attitude with it too. But it's attractive and it's got some attitude. So oxygen will attract those electrons more strongly than the hydrogen because it's like, I'm prettier and I need these. Thank you. No negotiations, I'm pretty and I need it. So the shared electrons spend more time near the oxygens because they need them. So that actually gives the oxygen a slightly negative charge because that's kind of not the nicest thing in the world to be like, I'm pretty, I need more of this. Thank you. Okay. And so it gives it a slightly negative charge. But the hydrogen's so nice to be like, all right, that's fine. You're going to be that way. You can have them. And so it's kind of nice and giving. So it makes the hydrogen of this thing slightly positive. So we call this a polar covalent bond because it forms two poles, so two opposite ends. Like the poles of a magnet, there's a pole, like a positive pole of a magnet and a negative pole of the magnet. That's kind of what happens here. And so there'll be some different attractive forces. Okay, so we'll come back to that. And we'll look at it when we talk about hydrogen bonds. So an ion is an atom or molecule with an electrical charge resulting from gain or loss of electrons. So hopefully you remember that. If not, it should be a review. So if you lose an electron, you subtract a minus. Like, what do you do when you subtract a minus in like math? Like 1 minus -4. It's like, well, that's silly. You just add them together and you get 5. So subtracting a -1 gives you a positive charge. When an electron is gained, so we're adding a negative. So if I have 1 plus a -4, so I'm adding a negative here, then I get a negative thing. So you get a negative charge. I think math. If that's screwy to you and they're like, oh no, not with the math symbol crap again, then just think electrons lost makes it a positive. Electron gained is a negative. Okay? That's just how I think, but it's up to you. So two ions with opposite charges attract each other. And this attraction holds the ions together. It's an ionic bond because you get a positive and a negative. And this is usually what I call a give and take relationship. And you're going to see why in just a minute. By the way, a salt is a synonym for an ionic compound. But it's a nice give and take relationship. There'll be a video, but we'll look at this. So when we talk about electronegativities, we'll go back to that. Electronegativity, remember that's how pretty it is. So the thing with this relationship in electronegativity is that the chlorine is very, very pretty. I mean, it's gorgeous. Like, it is a good looking atom. It's up there. You just put an insert pretty person here. Okay, and it just so happens that sodium is kind of ugly. Okay, so think about a relationship where you see two people together and one of them's really gorgeous and the other one's not so much. So what is the very pretty one probably getting from the not so pretty one? Probably money. Alright, well, it just so happens that the sodium has extra money that it can give to the chlorine in terms of like electrons, and it gives it to the chlorine to make the chlorine happy because it's so pretty. And since that's the case and it's so pretty, we're going to give, some money to it or whatever, so it'll stay. That changes this to a positive and a negative, and they're attracted to each other because, it just works that way. That's one of those relationships. These guys usually form what we call a lattice structure, and the fact that we've got a positive and then a negative and a positive. And so the negatives are always surrounded by positive, and the positives are always surrounded by negatives. So it just, they're attracted on either ends. We call it a lattice structure. Here's the last little one that we'll talk about is hydrogen bonds, and this will be important for the next section. But in living organisms, most of the strong chemical bonds are covalent, linking the cells together. So most bonds are covalent. But we also need some weaker bonds between molecules. And this is between molecules, between whole molecules altogether. One of those weak bonds is called a hydrogen bond, and we can look at it through water molecules. Because water molecules are, again, polar covalent. Meaning they're going to make two poles, two different sides. Okay, so there's a lot of words here, but remember it's a polar molecule. So unequal distribution of charges, which just means unequal sharing. Because the oxygen, because it's pretty, is taking more of its fair share of electrons than that hydrogen. So that makes the, a partial charge allows each hydrogen to be attracted to a nearby atom that has a partial negative charge. So the hydrogen is partially positive and the oxygen is partially negative. And so these things can attract to one another because of that. Okay, so hydrogen bonds, if you want to read through this, if you're more of a reader, this is a good time to pause and read through it before you move on. Otherwise, I'm just going to show you in the picture. Okay, but if you need to read something, you can either go back to it later or just look at it. Again, we'll look at the video later. But remember, this is the oxygen, and this is the hydrogen up here. So oxygen being slightly negative because it's a little greedier and takes more of its fair share is actually attracted to other molecules that have the hydrogen. So these guys actually kind of line up to one another. They're like, oh, how are you? You know, it's the opposites attract type thing. They get along a little bit better. So the negative and the positive can actually line up. And this doesn't have to last very long, and it's really weak. It's not any kind of solid bond, but a hydrogen will always kind of attract to the negative end of the oxygen. And they'll just kind of line up towards each other and kind of stick a little bit more. And we'll talk about that, how it relates to water's properties, kind of next time. Okay, in our next lesson together, we'll talk about those. So negatives and positives of these that are partial negative, partial positives, always line up so they can get there. Okay, so that way they all kind of stick together a little bit better. Last thing we'll talk about is just remember chemical reactions. If we were to use the reaction 2 hydrogen plus oxygen yields 2 waters. Remember the reactants would be over here. The hydrogen and the oxygen, those are the things that we react together. And water is the product or the thing that we produce. Chemical reactions don't create or destroy matter, they only rearrange it. Okay, and the best way to look at that is just through a nice picture. Same thing. We have 1, 2, 3, 4 total hydrogens, and we still have 1, 2, 3, 4 total hydrogens over here. With 1, 2 oxygens, 1, 2 oxygens. So nothing's created or destroyed, we just rearrange. And that is all, alright? The only thing I'll say about that is why chemical reactions are important. When we get to photosynthesis and cellular respiration and the 3rd unit, it will all depend on chemical reactions. And there's a lot, but they are chemical reactions that we talk about in terms of biology. Okay, so with that, that is the end of this particular lecture. You know, if you have any questions, shoot me an email. But we'll keep working and we'll get it done in the next class.